Welcome to a video lecture on nuclear physics. This one will cover chapter 31, so please make sure to follow along in the textbook. Let's begin. For every element, there is a certain number of protons, neutrons, and this here is given by the atomic numbers around it when you see like an element. So, for example, carbon has 6 protons, and a normal carbon-12 would have 6 neutrons. Also, carbon-14 would have 6 protons, but 8 neutrons. Now, the way these numbers work is A represents the number of protons and neutrons. It's the atomic mass number for an element. So the number of protons and neutrons for carbon-12 is 12. The number of protons and neutrons for carbon-14 is 14. It's how many total protons and neutrons. Now, what Z represents is really, and it says number of protons here, but I don't want you really to think that. It's more the total charge of the particle. And the reason, you'll see for a second why I say particle and not element or anything like that, but it's the total charge of the particle. And generally it is, when referring to elements, it's the number of protons in the nucleus, or the charge of the nucleus, you can think, but it's really the charge of the particle. So A is, again, the total number of neutrons and protons. Z really is the total charge of the particle. As you look at the symbols, you can see why I was saying that it's the total charge of the particle. So let's start at the top. A proton, really all it is a hydrogen atom that is stripped of the neutron, excuse me. So it just has one proton and neutron, and it has a charge. The particle itself has a charge of +1. There you go. You can see one proton and neutron, charge of +1 means it must be a proton. Next, we have an electron. There are 0 protons and neutrons of this particle, and it has a charge of -1. Now, the interesting thing here, when we talk about mass of atomic mass units, an electron has 0 mass. It has a negligible amount of mass when we're talking about protons and neutrons. Not completely negligible, but for our intensive purposes now, we're going to consider it negligible. Next, we have a positron. This is a positively charged electron because as we'll see here as we go through, there's things called antimatter, which means that each particle has what's called an antiparticle, which is the opposite of it. So an electron has an antimatter particle, which is a positron. We generally don't see these very often because what happens is, and this is what I did some of my thesis work on, they annihilate each other and they create 2 photons that go shooting off. Won't have to worry about that too much. Positron, pretty much straightforward. It's a positive electron. Next, we have a neutron. Neutron, as we see here with the numbers, looking at the numbers, not focusing on the symbol so much, it has 1 proton and neutron, but it has 0 net charge. So since it has 1 proton and neutron, but 0 net charge, it can't be a proton, so it must be a neutron. So therefore, it has a charge of 0, and its mass is essentially 1. We'll talk about this a little bit in a second. Mass defect is really the difference between the mass of the individual particles that make up a molecule and the total mass of a molecule itself. So if we look here, helium-4, it has 2 protons, 2 neutrons, 2 electrons. Individually, those particles have more mass than that set molecule. So there's what's called some binding energy that holds all those particles, together as one individual molecule. Now, that binding energy is really that it's the difference in mass between the particles and the molecule, and it's also that binding energy relates to the amount of energy it is needed to split them apart. This here comes from Einstein's famous equation, probably not his most important or easiest to understand. I guess it's the simplest equation or the simplest concept that Einstein came up with. Maybe, I don't even know. But you would go through and you add up the different amount of mass from each individual particle, and you take that and you subtract that from the atomic mass of the set molecule, and you get the difference in mass multiplied by the speed of light, or you could use that one atomic mass unit is 931.5 mega electron volts per speed of light squared, and this gets you the amount of energy that it takes to bind the molecule together, bind the nucleus. Once again, a lot of these things are shown on your formula sheet, so you shouldn't have to memorize too many of these. There are three different types of radioactivity that we'll be concerned with. Probably the first two are really the most important ones. They involve a change within the nucleus itself, either a proton or a change in the number of neutrons there. So alpha decay is actually what's happening is the element itself is changing, so there's a proton that is leaving. In beta decay, what's happening is there's an extra amount of neutrons, and the neutrons are decaying into different particles, and they release other particles with them. And then finally, in gamma decay, we have excited states similar to an electron, and as we talked about before, and this releases a very high energy photon in the form of gamma radiation, but it's the states of the same element when this happens. Many large nuclei are very unstable, and what happens when they're unstable is they will decay and energetically break apart into smaller particles. And what happens is they release what's called an alpha particle. Now, an alpha particle is just really a helium nucleus that's been stripped of all its electrons. It has a positive 2 charge, and it is released and moves off. So you have some parent nucleus that has a set number of some isotope of, say, a higher thing, like, for example, in smoke detectors, you have americium. I believe I pronounced that correctly. And that decays into neptunium and releases an alpha particle. And what happens within this is the decay, the extra protons leave decay, meaning that it moves into a different element itself. It changes elements. There's also some energy released, and this gives it to the alpha particle. This energy gives the alpha particle some motion and shoots it off in some direction. So there's so think of it as kind of an explosion from in a momentum explosion. There is the recoil of the daughter nucleus, but the alpha particle is kind of shot off at a very high speed. And what happened, and further on, that alpha particle interacts with other particles and causes them to different things, as we'll see in a little while. But this is alpha decay, where there's a parent nucleus decaying into a daughter nucleus plus an alpha particle, which is just 2 protons and 2 neutrons stuck tightly together, plus some energy which is given into the helium nucleus itself. There are 2 types of beta decay, beta plus and beta minus. In both cases, a neutron, and within the nucleus, it's generally an unbound neutron, is decaying into one or more particles. It's decaying really into 2 particles. In beta minus decay, what happens is the neutron decays into an electron and a proton. So it actually will gain a positive charge in the nucleus, but it ejects an electron. And this electron, and also there's included some energy here, and it will change from one element to another. So you have a parent nucleus and a daughter nucleus, once again. And this electron is ejected. There's energy. There's probably some photons or something else along that is some other radiation forms, maybe some X-rays, anything like that. Then there's also some within the beta plus decay. What it does is it decays into a positron. So actually the number of protons or the positive charge within a nucleus decreases by 1, and you're ended up with this antimatter particle, which will then very quickly annihilate with an electron or an extra electron. So this is the difference between beta plus and beta minus decay, is that the type of charge produced and the resulting charge of a nucleus. Now, boron number, let's say boron 12, 5 protons, it can undergo beta minus decay, and so that means that a nucleus changes into a proton and ejects an electron, shoots an electron off, and now it becomes, for example, carbon with 6 protons. This here is an example of beta minus decay. Gamma decay is similar to what we've seen before with the excited states of electrons within their different levels. The nucleus itself also has different excited states, and when it goes from an excited state to a lower state, the idea of taking a step down, there's some energy released. This energy is released in form of a very high energy photon. This is a gamma ray, very dangerous to humans, but there's no change within the element itself. There's no, the element remains the same. There's no change of the number of protons or neutrons, but there's just it's changing from one state to another. Most or many large nuclei are unstable and go through radioactive decay. And they don't necessarily decay into something that is stable. Now, each element has what's called a certain amount of half-life, and the half-life refers to how long it takes for the element to decay halfway into whatever the daughter nucleus is. So that half-life may be a couple of seconds, it may be days, it could be, there's a lot of different half-lives out there for what they will decay into. Now, on a decay series graph like this, you have two different things. You have the alpha decay. Alpha decay is when it's moving to the left. That's down and to the left because it's ejecting a alpha particle, 2 protons and 2 neutrons, so it's moving 2 spots to the left. And then you have beta decay, where this is really for beta minus decay. You are moving 1 spot to the right because it is decaying. The neutron is decaying into a proton. That's for beta minus decay, at least. So this is just a chart or graphical representation for the series of something that for materials, elements and what they decay into down till when they get something stable, which is generally lead. All right, for tonight's first question, I would like you to explain in your own words what is the difference between alpha and beta decay. I want you to use your textbook to help. If you want to go on the internet, that's fine too. But I want you to write more than a sentence and maybe more than 2 sentences, but I want it to be a very thorough answer here of just going through and explaining, thinking about this and kind of summarizing what I just talked about in this video. And I understand this is a longer, less exciting video, but just go through and summarize. Thank you very much. Have a good night.